One of the applications of double integrals involves distributions. Now, distributions are functions which describe certain properties of, for instance, the distribution of charge will describe how the charge is varying from one point to another, and with its help we can calculate interesting properties such as the total charge or the electric field of just with the distribution and some integrals. With this, also the same thing goes for mass distribution. You already know mass distribution in the term of density, and you can use mass distribution to calculate where the center of mass is, or how the mass, what the total mass of the body is, and other interesting properties such as the moment of inertia. And then there is the probability distribution, which has applications in many fields such as machine learning or quantum mechanics. And let's move on to distributions in one dimensions. So an example is the linear charge density. So if we have a charge which is across a line, for instance like an antenna, then we need to move through all of these points which lie on this line. Now, in order to move through a line, all we need is just a single integral. It means that our domain of integration is going to be a single integral, which will give us some interesting properties. We also have similar concepts of mass density, where the density of mass will change as we move across the line, but we can only move across the line. And interesting thing to note here is that all of this linear densities will have dimensions which have per unit length. For instance, for linear charge density, we have charge per unit length, and for mass we have mass per unit length. So this per unit length part is important. And then next one, we move on to distributions of 2 dimensions. In examples include surface charge density or the surface mass density, and they also have the same pattern. Like now our integral will move on to the double integral. It was single integral before. So, and the domain of our integration is now an area, which is of course reasonable, because these points lie on a surface, in a 2-dimensional surface. We would need to use the double integral to cover all the points of this domain, and they will have dimensions of whatever it is per unit area. This area part comes from, because it was 1 dimension before. At the domain it was length, per unit length. Now it will be per unit area, as we would expect. And moving on, we'll have the volume distribution, where we need the triple integral. And for here you would also see the same pattern. Area now is this will be volume. One example of a domain which is like a volume is the cylinder. Like, points within the cylinder are in 3 dimensions, and if we want to integrate or in a way that will cover up all the points of the domain, we need to use the triple integral. Now we will show some examples on triple integral on the next week's lecture. For now, we will focus on examples of applications of double integrals. Start with surface charge density, and this is denoted by sigma x comma y. And in order to find the total charge, we have to consider the effect of every single point in our domain, or in this case the surface itself. Every single point of the surface. Let's say if this is our charge distribution, this particular surface D, we have to consider the effect of all of the points on D. This means that this point has some contribution towards the charge. Every point has, and so in order to consider all of them, we have to do the integration over the entire domain D of this charge density function. And this is a double integral, so it's going our region of integration is an area. So this is my total charge. We'll call it Q, and we'll use this to solve a problem. Here the question is, the charge is distributed over the triangular region D in the figure below, so that the charge density at xy, at the point xy, let's say if this point is x comma y, equals to xy. So now what we know from here is that the charge density equals to xy. Great. Measured in coulombs per square meter. This is what we would expect, that the charge density will have units of charge per unit area, and meter square is the unit of area. So this is all right. So now the question is asking us to find the total charge, which we'll just simply use the double integral over our domain D of the surface charge over the area. So let's just do a type 1 way of doing this integration. So let's start a line below all the curves, and we start it up. The first curve we hit is this line y equals to 1 minus x. This will be our lower limit. The second line it hits is y equals to 1, this horizontal line. So next we have to know how much will all the points cover from in the two extreme x values, or which are of course this one, the leftmost point, and the rightmost point. This means that the integration will move on from throughout this region, starting from x equals to 0 and ending at x equals to 1. So from 0 to 1. So sigma is xy times, and since we are doing a type 1 integration, this will be dy dx. So we'll do the y integral first, treating x as a constant. So this will give us xy squared divided by 2 dx, where we have to put in the limits 1 and 1 minus x. So you can take x by 2 common to get 1 squared, the upper limit, minus and 1 minus x squared, just put the lower limit, times dx. So now we take the half outside, we'll have x squared minus, and this will give me, okay, let's not do this, keep x, 1 minus, expand this, 1 plus twice x minus x squared dx. 1 minus 1 is just 0. So this is just a formula for this square, a plus b squared. So now we get 2x squared minus x cubed dx, and this is just half, 2/3 x cubed minus 1/4 x to the power 4, where we take the limits from 1 to 0. So if I take 1, I've got 2/3 minus 1/4. If I put in 0, the lower limit, I'll get 0 here. So this is just half. 3/4 is 12, so we get 12. 4/2 is 8 minus 3. So we have 5 over 24. This is our total charge. Now we'll move on to center of mass. So this is the formula for the x coordinate of the center of mass, where we double integrate over region D, x times the density function, and this for the y coordinate of the center of mass, where we double integrate y times the density function. And if we want to find the total mass of a sheet of a sheet, then we need to double integrate over the density function, just the density function and nothing else. So let's use this formula and solve this for the following problem. Find the mass and the center of mass of a triangular lamina with vertices 0, 0, 1, 0, 0, 2 if the density function is rho times this rho xy, rho is a function of x and y, equals to 1 plus 3x plus y. So let's first start with a diagram of how the laminar is going to look like. So we have one at the origin, which is 0 at 0 0, 1 point of the triangle, and the other one is at 1 0, which means here, and this one is at 0 2. Now we connect them to form our triangular lamina. This is our triangular lamina. So now we have to find the equation of this line, this particular line. Right, so we can use the equation of a straight line to find it. Let's take this point, y minus 0 equals to m, which is the gradient of this line. So let's take 0 minus 2 y2 minus y1 divided by x2 minus x1. So we take this 1 minus 0 times the x coordinate, x minus x coordinate, so x minus 1. This will give us y equals to 2 minus twice x. So this is the equation of this particular line. Now let's find the mass. So mass is the double integral over the region D of just the density function times dA. So we'll do this with a type 1 integral. You can do this region also with a type 2 integral. So now we will start a small arrow from the bottom of the graph, and as it moves up, it should cross the region, and the first line it hits is y equals to 0, or the x-axis. This let's draw it. Let's give it a different color. This is the first line it hits, and this is y equals to 0. So we know our lower bound is going to be y equals to 0. Next, as it moves along, the next line it will hit is this line over here, y equals to 2 minus twice x, and all of this region, if they're filled up with vertical lines, they are all contained from 0 till 1, and this will cover the entire region of our integration, or the triangular lamina. Now our density function is 1, here is the density function, 1 plus 3x plus y times, we do the first integral we do is with respect to y, the second integral we do is with respect to x, because this is how type 1 is set up. So let's do the y integral. We'll then have y plus 3x y plus y squared over 2 dx, and we have to integrate from 0 to 2 minus twice x. So now we substitute the limits. Two minus twice x plus 3x into 2 minus twice x plus half times 2 minus twice x whole squared, and then all three have y, so 0 will give a minus 0, which I'm not going to write. So let's simplify this a little bit. Let's take 2 minus twice x is common. So we have 1 plus thrice x plus half times 2 minus twice x will be dx, and the dx, Now we can simplify the right part a little bit. So half times 2 is just 1, so we've got 2 plus 3x minus x. 3x minus x is just twice x, because a half times minus twice x is minus x, so we get 3x minus x, which is plus twice x dx. It's just 4 square, 2 square is 4, this is a square minus b square, so a plus b into a minus b, so we get 4 minus 4x squared dx. This is just 4x minus 4 by 3x cubed with the limits 1 to 0. So at 0 everything dies out, so we won't have to worry about this. So we put 1, the upper limit, so we get 4 minus 4 over 3. 1 to the power 3 is just 1, so now we have 8 over 3. Find the center of mass, the coordinates for the center of mass. So let's start with the x coordinate, and we know that the formula for the x coordinate is 1 over the mass times the double integral d of x times rho x comma y dA. So we know 1 over m is going to be, since m is just what we calculated a while ago, is 8 over 3, so this will be 3 over 8 times the double integral x times rho. Rho is just 1 plus 3x plus y. Then we'll again do it in type 1 integration way. So we have dy dA. Let's write the limits in the next line. dA. Now we already found the limits here. The region is still the same, no matter if we find at the x coordinate or the y coordinate of the mass. So these limits will also work, which we already found. So we do 0 to 2 minus 2x, this one, and 0 to 1. I just take x plus 3x squared plus yx, or just write xy, times dy dx. We do the y integral first. So this will be x times y plus 3x squared y plus xy divided by 2, y squared divided by 2. Now this we have to use the limit 0 to 2 minus twice x dx. So we got an x common here. 2 minus twice x coming from y plus 3x times 2 minus twice x plus half, because we took x as common, 2 minus twice x times dx. Sorry, that would be squared. This is a y squared. So here again we should take 2 minus twice x as common to make our life a little easier. So now we'll have 1 plus 3x plus half into 2 minus twice x, and let's just divide by 2 because then we'll have 1 minus x, because the 2's cancel, and times dx. And simplify this a little more. It's 2 minus twice x times 2 plus twice x dx. Again, we can use a square minus b square formula. 4 minus 2 minus 4x squared dx (4x minus 4x cubed dx). So let's just simplify this. 4, we have 3, then we'll have 3 over 2, because 4 to is 8, 4 into is 8, so 0 to 1, x minus x cubed dx. Now let's take the integral. We have 3 over 2 half x squared minus 1/4 x to the power 4, starting from 0 ending at 1. Then we put 1 to get 3 over 2 half minus 1 over 4, and this is just this part is 1/4, so we've got 1/4 times 3 over 2, so we will have 3 over 8, and this is our x coordinate value for the center of mass. Now let's try and find the y coordinate of the center of mass. The y coordinate of the center of mass is just 1 over the mass, the double integral over the region D of our density function times dA, and of course we have to multiply it by y, and 1 over m is actually 3 over 8, because our mass is 8 over 3. We inverted, we get 3 over 8. Next, we still have the same region, so the limits for our integral will not change, and that means this is going to be 0, 2 minus twice x, and this one 0 to, let's say 0 to 1. It's the same limits for all three integrals in this case, since we're still trying to solve this with type 1. So it's y into, see what the density function is. This is the density 1 plus 3x plus y. We have 1 plus 3x plus y dy dx, because we did the y integral first. This is y plus 3xy. Okay, let's just keep the y terms together. So we got y times 1 plus 3x plus y squared dy times dx. We have to multiply this with 3 over 8, 0 to 1. Now we integrate. Oh, sorry, there will be a 0 to 2 minus x. We still haven't done the integration. So now we integrate the y part, keeping x, anything in x constant. So we will have y squared divided by 2, 1 plus 3x plus y to the power 3 divided by 3, and we take the limit from 0 to 2 minus twice x times dx. So now let's put in the limits. So we'll have 2 minus twice x whole squared divided by 2 times 1 plus 3x plus 2 minus twice x whole cubed divided by 3. This is to be integrated with x. So we've got 3 over 8, 0 to 1. We can take 2 minus twice x whole squared as common. So we'll have 1 plus, okay, let's take the fractions outside before we do this. So we have, if we take the fractions of both, then we have 6, right? 2 into 3 is 6, and here we'll have 3 times, and here we'll have 2 times, and then we can also shift the 1/6 part outside of the integral, so we don't have to worry about any fractions. So this will have, we got a 3 over here, so 3 plus, sorry, no, we don't take the 3. We got 3 times 1 plus 3x plus 2 times 2 minus 2x. Now we just we have 2, like 3 into 2 is 6, right? So we got 2 into 8 is 16th. Oh, there will be a dx here. So 3 plus 9x plus 4 minus 2 into 2 is again 4x dx. Zero to 1. We have got 4 minus 2 into 2 into 2 is 8. 8x. Okay, let's simplify this before we go into that. So this is 3 plus 4 is 7. 9 minus 4 is plus 5x. So 4 minus, let's now go back here. So 4 minus 8x plus 4x squared times 7 plus 5x. Multiply it out. 4 sevens is 28. 4 into 5 is 20 plus 20 minus 56x. 8 into 5 is 40, so minus 40x squared plus 28x squared plus 20x cubed dx, which is equal to 1 over 16. Let's simplify it out before we integrate. Minus 36x. Okay, so minus 12x squared plus 20x cubed dx. Now we'll get, after the integration, we'll have 28x minus 18x squared minus 4x cubed plus 5x to the power 4. Use the limit from 0 to 1. It's just 1 over 16. Since putting 0 will make all the terms 0, we'll only be concerned with the upper limit. 28 times everything times 1 is itself. Minus 18 is 10. 10 minus 4 is 6. 6 plus 5 is 11. So our answer is 11 over 16. So now we state that the center of mass has coordinates the x coordinate is 3 over 8. This was our x coordinate, so this is 3 over 8, and here we have the y coordinate as 11 over 16, which you just calculated. It's 3 over 8, 11 over 16. Yes.